Hello everyone. My name is Amir Hakshanas and I'm a PhD student at Dorsal. I've started my PhD in the summer and I'm working with Michel and Nasser on cost-aware tracing. So let's have an overview on what I'm going to present. First, we will see the problem statement and then we will have a quick look at some of the related researchers to mine. The next step, I will discuss what I've done and what I'm working on, and then the last one is my future work and the next step for my research. So as we all know, tracing can generate a large amount of data in very limited time. But there is a problem that it is not always possible to trace and save everything. For instance, in IoT devices and embedded systems, we have lots of limitations on the resources, such as the memory is very limited, and sometimes the execution time is really crucial, and we cannot have so much delay on the execution time. So we need a solution to help us choose how to collect as much as data possible according to the limitations that our system has, especially in the systems with limited resources. So this solution should consider the observer effect of tracing on the program that is under analysis. And by observer effect, I mean the cost that the tracer add to the program execution, such as the execution delay or the memory consumption. So to solve this problem and to answer our question, one way or one good way is to define a budget and see how much overhead is acceptable for our tracer. And based on this budget, we can work with the amount of data that we can capture or we can save or we can send to a server. Aside from sampling, we can use this cost or the effect to actually choose what data to capture or what data to eliminate. One solution is to just do it based on the cost. So I mean that just remove the trace point or remove the tracer with the most execution delay or the most memory consumption, and the other one is to use the effectiveness of the data that we have or the effectiveness of the trace points that we have, and keep the most important data and then just eliminate the rest which are not that important. Studies related to what I'm working on can be divided into two groups. The first one is the studies that analyze the observer effect of tracing, and they calculate and measure this observer effect. One of them is actually a paper that was done in the lab, which they performed a survey on kernel and user space tracing, and they captured and visualized the overhead of each trace point on the program. They calculated the execution latency of a single trace point using the kernel modules, and then they provided the metrics that can be related to each execution latency of the trace points. The more recent paper was focused on the analysis of the effect of tracing on the concurrent behavior of a program. So what they did is they provided or they proposed a configurable overhead tracer, and with that they were able to add overhead to something like the memory usage or the CPU usage of each trace point. And then they applied a concurrent performance analysis to see how much these overheads can affect the concurrent behavior of the system. The second group can be known as the studies that use this cost and provided a cost function to modify their tracing based on the budget that they have. So the first study that actually introduced time-aware instrumentation has a optimization model that the objective function is actually the instrumentation coverage, and the cost function is the execution time. And they first start with a naive instrumentation, which means they instrumented everything and they captured everything. And they will analyze and monitor the execution time of the system. If this execution time violates the budget that they have, they will use a integer linear programming to reduce this coverage to meet their budget. Another paper worked on a static instrumentation model called InStep, and this is somehow a similar approach, and their objective function was the intent values for instrumentation and the values that they want to capture, and their cost function was code size, execution time, and the detection delay of this value that they want. So this was completely a static instrumentation, so they would create an automata to represent a cost model for each of their cost function. And what they did was try to provide an insight into how to prune the search space to find the best feasible instrumentation solution for their problem. The same team actually presented another paper in dynamic binary instrumentation, which is called DIME. This paper focused on time-aware instrumentation. And what this does is they keep two versions of a program. The first version is the instrumented version, and the second one is not instrumented. And they will define two elements. The first one is the instrumentation period, and the second one is the instrumentation budget that they have, which is always going to be less than their period. And for each period, they will only instrument their program for the B or the budget time unit. And then after they exceed this budget, they will switch back to the non-instrumented version, and they only have data for the time that they actually monitor the program. So let's see what my research is about. My objective is to define a budget for tracing overhead and then monitor the system in real time. After that, I'm going to define a model for cost of tracing and also for effectiveness of tracing, and I will focus on each trace point that is enabled. And finally, I will create an optimization model and optimize the cost and effectiveness of the tracing that we have. So what I did so far is that I decided to work on execution delay of tracing. So my cost function is the execution delay of each individual trace point. And right now I'm doing the measurement and visualization of this cost. For the measurement, I'm actually working on two possible ways. The first one is to develop a kernel module to record trace point execution time. And the second one is using perf events to actually record the kernel counters, and using that get the execution time of each trace point if I can. For visualization, I decided to work on the Trace Compass. So I've cloned a local version of Trace Compass and I built it, and right now I'm working on the histogram view to show the execution delay of each trace point instead of the event count that it's already presented. The future work of my research is to first change the histogram view, which I've heard that it's a very old view, to a cost analysis view that users can select different cost functions and observe the cost of tracing for each cost function. And then define a model for tracing effectiveness, which can be the coverage or anything. And then modify the budget that we have, which is right now time budget, that or make it actually, it can be a static budget, which could be like a fixed added time, like I don't know, 100 millisecond or something, or it can be related to the current workload of the system. So the final step is to actually develop the optimization model to minimize the cost and maximize the effectiveness of this of the tracing. And these are some of the references that I used in my presentation. Thank you for your attention.